Okay, so let us continue our discussion on doping of silicon substrate, and as I was telling, doping is necessary to modify the electrical conductivity of silicon substrates. Okay. So let us look at here, as we were discussing, the dopants are diffused into silicon substrate typically in a thermal furnace where the temperature is between 950 to 1280 degree centigrade, and the diffusion of dopants is governed by the Fick's first and second laws. Okay. Fick's first law says that the dopant flux is proportional to the concentration gradient and d is the diffusion coefficient. Okay. And as we discussed, the negative sign is because the concentration decreases along with depth. Okay. So if this is the surface of the substrate, x is into the substrate. Okay. So as the concentration reduces with x, there is a negative sign here. Okay. Fick's second law tells that the flux gradient del f over del x is proportional to the change of concentration with time. Okay. So del f over del x, as you see here, is equal to del c over del t. Now if you substitute the expression for f from Fick's first law, we can write it as d, which is diffusion coefficient, into del square c over del x square. So it is a second order differential, second order in space and first order in time. So here we would need two boundary conditions, as you can see here. Here we are assuming that in the first case we are assuming that the surface has the concentration of the dopant at the surface doesn't change with time. Okay. Which means that there is an infinite supply of dopant at the surface. Okay. So what it means mathematically is that C at x equal to 0 and any time equal to Cs. So that is a constant value at the surface, and C at x equal to infinity for any time is 0. Okay. Because the concentration would reduce to 0 as we go away from the far away from the surface. With these two boundary conditions, the equation can be solved. So this is the solution, okay, for Cxt. Cxt is Cs into complementary error function of x over square root of 4 dt, and we said that the square root of dt is the diffusion length, and we can define a parameter lambda, which is the characteristic diffusion length, as square root of 4 dt. Okay. And this characteristic diffusion length is the distance where the concentration will be reducing to 0. Okay. So it is the distance from the surface where the concentration will reduce to 0. Okay. Now knowing the variation of concentration with x and t, we can find out the total amount of diffusion that occurs from outside the source into the substrate. So you can find Qt as 0 to infinity Cs, a complementary error function of x over square root of 4 dt into dx. Okay. So we integrate throughout the depth. So if you do that, we get an expression for the total dopant diffusion. So total doses is directly proportional to the concentration at the surface, and it is also directly proportional to square root of t, okay, which is time. Now instead of assuming that the concentration remains fixed at the surface, if you assume that there is a definite amount of dopant available, okay, Q, which is the total amount of dopant available and which reduces with time, so there is not an infinite supply of dopant, then the solution is going to change. Okay. So that is the second case that we will be looking at, where we assume that the dopant concentration at the silicon surface is limited. Okay. So we have a fixed amount of dopant that is present at the surface, but the condition that C at x equal to infinity t equal to 0 will be valid, and the second boundary condition is that q is constant at the surface. Now if we use these two boundary conditions, then the resulting dopant profile, okay, the variation of the concentration of the dopant with x and t will be Gaussian in nature, okay, whereas in the previous case it was a complementary error function. So Cxt will vary as q over square root of pi dt into exponential minus x square over 4 dt. Now here if you plug in x equal to 0, which is as the surface, then you get the surface concentration, which is not constant but a function of time, okay. So that is the difference between the first case and the second case. Here the surface concentration is not constant but a function of time, so it reduces with time as 1 over square root of t. D is the dopant diffusivity, as I was telling, and you can express the dopant diffusivity in this form from thermodynamics. So D is given by d0 t0 into exponential minus Ea over kT, where Ea is the activation energy, and that depends on the transport mechanism, and the typical value is between 0.5 to 1.5 electron volt, and d0 is a constant, for a given reaction and concentration. T0 is the temperature, and K is the coefficient that depends on the diffusivity regime, and typically it has a value between 1.6 to 0.87, okay. So this is where we see two different cases that we just discussed. We are plotting the variation of the concentration with x, okay, how the concentration is changing with x and as well as t. So here on the x axis we have x over 2 square root of dt, okay, and y axis we have c over cs. For the first case the solution is the complementary error function, so that is the nature of the curve as you see here, and for small distance from the surface, when x is of the order of let us say square root of dt, then we can see that the curve is linear, that means the concentration varies linearly with the depth, okay, and this is the curve when the dopant concentration is not fixed at the surface, but there is a definite amount of dopant present, okay. So the curve is Gaussian in nature. Now the another approach to do doping is by ion implantation, okay. So by diffusion based doping, always the concentration of the dopant reduces with x, okay, and if you want to dope at a particular depth, it is not possible, it has to always start from the surface, go into the depth. However, if you can use ion implantation method, it is possible to dope a particular section of the wafer at a particular depth, okay, and that is possible because you are using high energetic dopant ion which can penetrate the depth of the wafer and locate at a particular depth, okay. So the advantage of doping by ion implantation is shown here. It has the ability to place any dopant ion at any depth that we want, so it is not dependent on the thermodynamics of diffusion that we had seen in the previous cases. So in this case, in ion implantation, the beam of energetic ions are implanted, and these beam of energetic ions would implant the charged dopants at a particular depth, and the depth and the dopant concentration will be controlled by the acceleration energy and the beam current, okay. So the acceleration energy and the beam current of this beam of energetic ions would control the dopant concentration and the depth. and we can selectively dope different areas by using mask. Okay. The one downside of ion implantation is that since we are talking about highly energetic ions, okay, that would create crystal damage in the wafer. Okay. So we are using high energetic ions to dope a particular type of dopant at a particular depth, but we are talking about high energetic ions. So they may create crystal damage, but it is possible to reduce the crystal damage, to take care of the crystal damage by annealing. Okay. So if you can anneal the substrate after the ion implantation at 700 to 1000 degree centigrade, you can overcome the crystal damage. So in the context of ion implantation, there are few terms that need to be defined. The first term is the projected range. So the projected range is the distance, the average distance travelled by the ions parallel to the beam. Okay. So if you have a substrate surface here, how much distance the ion is penetrating into the wafer parallel to the beam is called as the projected range. And the second term is projected straggle. So it is the fluctuation in the projected range. So if you target, let us say this as your RP, and there is some variation around RP, that is known as the projected straggle. The lateral straggle is the fluctuation in the final rest position normal to the beam. So how much variation you would get in a direction normal to the beam direction is known as lateral straggle. And peak concentration NP is the concentration of the implanted ion at the projected range. So if this is the projected range, the peak concentration would occur at the projected range. Okay. So here in this case it has been found that the concentration profile is Gaussian in nature. Okay. So this is the equation by which you can express the concentration, how the concentration of the doping varies. So this is the formula here. Ni is the implanted atoms. Okay. So this is the number of atoms that are implanted, number of dopant atoms that are implanted, and Qi is the total dose, and we already have defined Rp and delta Rp, which are the projected range and the lateral the projected straggle, and x is the depth. Now we can, knowing Qi, so Qi would be, so it is basically the total current, total ion that you are depositing or doping into the surface, into the substrate. If you integrate with time, that will give you the total dose that is being implanted into the substrate. Now if you divide that with the charge per ion, which is Zq, and the area over which this implantation is being done, then that is known as the dose. So it is expressed in the form of atom per centimeter square. So with that let us move on and talk about oxidation of the silicon. Okay. So we clean the wafer, then we dope the wafer if it is required. It is relevant for electrical application where we are relying on the conductivity of the substrate, and then the next step would be to grow an oxide layer on silicon. Okay. And this oxidation is typically done in the oven, the furnace, oxidation furnace, and there are different techniques. It can be either wet oxidation, it can be dry oxidation, or it can be pyrogenic oxidation. Okay. So typically the oxidation would involve heating of the wafer in a stream of steam in case of the stream of steam in case of wet oxidation, that is typically done at 1 atmosphere, or in wet or dry oxygen and nitrogen mixture at about 600 to 1250 centigrade. Okay. So this is the a typical process that is done in a furnace, oxidation furnace. So the silicon, if you expose a typical silicon substrate to air, it would always have an oxidation layer on the surface, it would oxidize. Okay. However, if you subject it to high temperature, then you can grow thicker oxide layers. Okay. So if you want to grow thicker oxide layer, you have to subject the wafer to high temperature. Okay. So silicon oxidizes at room temperature, and at high temperature the diffusion of oxidant through the surface oxide layer will happen to create the thick oxide layer that is required. Now if you start with a silicon wafer, as you can see here, let us say this is the silicon wafer, and you put it in an oxidation furnace. Now let us say you have silicon dioxide layer growing on both sides of the wafer. Let us consider only one side. Let us say the total oxide thickness is specified by x. Okay. Now if the total thickness is x, about 0.46 of 46% of the total oxide layer will be the consumed silicon. Okay. So the silicon dioxide, so the oxidation occurs both into the silicon substrate as well as above the silicon substrate. So if you have grown, let us say 1000 micron of silicon dioxide on a silicon wafer, then 400, let us say 1000 nanometer of silicon dioxide on a silicon wafer, 460 nanometer of silicon, thickness of silicon has been consumed. Okay. And you have 500, another 540 nanometer has been grown on the surface. Okay. So you can see here in the oxidation process, the thickness of the silicon that is consumed is 0.46 times the total oxidation oxide thickness. Okay. So if you have 10,000 angstrom of oxide has grown, 4,600 angstrom of silicon will be consumed in the process. Now the oxidation is typically a 3-step process. As you can see here, this is the silicon substrate. So as you can see here, this is the silicon substrate, and this is the oxide layer which is the next to the silicon substrate, and here is the gas, okay, that is exposed, either it is gas or steam depending on the type of oxidation furnace you have. And the 3-step processes are shown here, F1, F2 and F3. Okay. The first step is the gas phase transport of oxidant to the surface. So you have the gas phase here, the oxidant have to be transported from the gas medium to the surface of the top surface of the oxide layer. Okay, that is the first step. Then the second step, the oxidant have to diffuse through the existing oxide layer. Okay, say this is the concentration of oxidant on the top surface. Okay, and it will reduce to the oxidant concentration will reduce to Ci on the top of the silicon. So the oxidant have to diffuse through the existing oxide layer, and the third step is the oxidation reaction at the interface. So the oxidation reaction always happens at the silicon dioxide interface. Okay. So the oxidant have to come to the top of the silicon dioxide surface, they have to diffuse to the existing silicon dioxide layer, and then the oxidation reaction have to start at the silicon dioxide interface. Okay. So F1, the diffuse the transport of the oxidant to the surface is governed by this equation, H into C star minus C OX, where H is the gas phase mass transport coefficient. Okay, H is the gas phase mass transport coefficient, and C star is the equilibrium oxidant concentration in the oxide, and Cox is the concentration of the oxidant in the on the oxide layer. Okay. Now C star is can be thermodynamically expressed as H into partial pressure of the gas phase, and H is called the Henry constant. Okay. F2, since it is diffusion through the existing oxide layer, it will be governed by the Fick's first law of diffusion, and that is given by D into the concentration gradient, which is COX minus Ci over X, the thickness of the oxide layer. And F3, which is the oxidation reaction at the interface, that would depend on Ks. Ks is the oxidation rate constant, and Ci is the concentration of the oxidant on the silicon and silicon dioxide interface, okay, at that very interface there. So those three are the three different steps in a typical oxidation process. Now if you equilibrate all these three fluxes, F1 equal to F2 equal to F3, then you can find the expression for the concentration of the oxidant at the silicon and oxide interface. So the concentration of the oxidant at the silicon oxide interface is dependent on these parameters, okay. It depends on the oxidation thickness, the oxide layer thickness, it depends on the rate constant, it depends on the diffusion coefficient and the partial pressure of the oxidant in the gas phase. So the oxide growth rate, how the oxidation thickness changes with time, it has been found that the oxidation growth rate can be expressed as Ci, which is the concentration of the oxidant at the silicon oxide interface, into the rate constant divided by N, where N is the number of molecules of oxidant per unit volume of oxide, okay. And typically it has a value of 2.2 into 10 to the 22 per centimeter cube for dry oxygen, and it has a value which is about two times for wet oxidation, so about 4.6 into 10 to the 22 per centimeter cube for wet oxidation. Now if you seek a solution to this equation here, there are different models available, and one such model is the dual groove model, and using dual groove model the expression for the oxide layer thickness with time can be found. So this is the expression for how the thickness of the oxide layer changes with time. So it is A over 2 into 1 plus 4b into t plus tau over a square half minus 1, where A is given by 2 into diffusion coefficient into 1 over rate constant plus 1 over the mass transfer coefficient H, and B is 2 into diffusion coefficient C star over N, and tau is the time constant which is given by xi square. So initial oxide layer thickness square plus A into xi is the initial oxide layer thickness divided by B, and H is the, we have already defined, is the mass transport coefficient, and xi, as I said, is the initial oxide thickness. Now if you consider that the oxide layer is very thin, that means we are talking about the beginning of the oxidation, then we can say that here, as you see here, for the oxidation time when it is small, then t plus tau in this equation, t plus tau will be small compared to a square over 4b, and if that is the case, then we can use expand this, we can bring half as a coefficient here. So you can find the oxide layer thickness as a function of time, which will be b over a into t plus tau, and if you plug in the values for b and a, we would get c over n into 1 divided by ks plus 1 over h minus 1 into t plus tau. So what you see here is that the oxide layer thickness is linearly varying with the time, okay, and that is at when the oxide layer thickness is small, okay. And here the B over A, the ratio B over A as you see here is a linear rate constant which has unit as micrometer per hour. On the other hand, if the oxide layer thickness is large, where T will be greater than the time constant tau, and so T will be greater than A square over 4B, then you can work on that equation to show that you can reduce the equation as into this form. So square of the oxide layer thickness with time will be B into T plus tau, and if you use the expression for B, you can show that is 2D into C over N into T plus tau. So what we see here is that the oxide layer thickness would increase linearly with time at the small times, and at a larger time it is going to be parabolic in nature, okay. So the oxide layer thickness will increase parabolically, okay, and this is what we see here at at small time scales, okay, at thinner oxidation layer thickness, the oxidation would depend on the rate constant, okay, the rate constant at the silicon oxide interface. At large time scales for thicker oxide layers, because you would have already built thicker oxide layers for large times, the oxidation will depend on the diffusion, okay. So first the oxidant has to diffuse through thicker oxide layer, okay. So that is what we see here, and the combined oxidation rate, the case where it is the reaction rate limited and the case where it is diffusion limited, we can combine the two to find an expression, generic expression that can be applied for any time. So this is a generic expression which is square of oxide layer thickness plus A into oxide layer thickness is B into T plus tau. So the combined oxidation rate would depend on the crystallographic orientation, okay. So depending on the orientation of the oxide the silicon substrate, the oxidation rate will vary. So typically it has been found that the oxidation for a 110 wafer is greater than 111, and that is greater than 100 wafer, and the oxidation is also going to be affected by the doping, how we are doping the wafer, the impurities that are present on the substrate, water or hydrogen, depending on how we are going to oxidize the wafer, and the gas pressure. So these are different parameters that would affect the oxidation rate. So typically this is one model that you can use to predict the thickness of the oxidation layer. Alternatively, you can use tools like ellipsometer to predict how it's a optical technique that can be used to measure the thickness of an oxidized wafer, okay. And you can also use color table to get an approximate idea of how thick the oxide layer is, okay. So here is what we have discussed. You can see we are talking about how the thickness oxidation thickness is varying, and on x axis we have time, and this is a case where this is valid for smaller oxide thinner oxide layer, or when the time is less, okay. So small times this equation is valid, and at large times when the oxidation is diffusion dependent, this equation is going to be valid, okay, and this is rate constant dependent. Now this gives a combined equation which can be valid for any time scale, okay. Now here you see a color chart, depending on here on here you have the oxide thickness in angstrom, and here you have different colors that are shown, and there are, for each color there is a color code associated, and here you have, this is a description of what color that you see. So typically you oxidize a wafer, take out of the oxidation furnace, and you can have a look. There will be a color chart available. Depending on how you can judge the color, you can predict the thickness of the oxidation layer, okay. So as you can see in the table, for example, you take out the wafer from the oxidation furnace, and you find that the surface looks blue, okay. So if the surface looks blue, you can say that the oxidation thickness is about 3100 angstrom, and for example if the surface is looking brown, you can say that the thickness is 750 angstrom. So this is an approximate, but it is a quick approach to measure the oxidation thickness, okay. Now here we take an example of how to predict the thickness of silicon dioxide layer. As you can see, here we have a silicon substrate, and on the silicon substrate initially we have an existing silicon dioxide layer which is 4000 angstrom, and we put this pre-oxidized silicon wafer for steam oxidation or wet oxidation in a furnace at 1100 degrees centigrade for 33 minutes, and we get some oxide thickness, and we want to predict what is going to be the thickness of the oxidation layer after 33 minutes. So there are two approaches to do that. One is there are oxidation charts available. The second approach is to use the equation that using the Dilgrove model, okay. Now if you use oxidation chart, which is here that you see, and this chart is valid for Xi equal to 0, that means there is no existing oxide layer on the surface, and based on that condition, on the x axis we have oxidation time in hour, and y axis we have oxide thickness in micron. So in our problem we say that there is an existing oxide layer at 4000 angstrom. So for the initial oxide layer thickness, if you look at the oxidation chart, so this is an extract from the oxidation chart that I just showed you. For if for 4000 angstrom and temperature being 1100 degrees centigrade, okay, so this temperature is what we are going to use for the existing oxide layer thickness, but for the existing oxide layer thickness, if that were grown at 1100 degrees centigrade, assuming that it were grown at 1100 degrees centigrade, what would have been the time? So the temperature is 1100 degrees centigrade, thickness is 4000 angstrom, so you can say that if on the x axis the time is going to be 24 minute. So similar thing that you can observe in the chart. So if you say that your oxide thickness is about 0.4 micron, so this is 0.1, so this is about 0.4, and 1100 degree, if you draw a horizontal line here and you draw a vertical line, is going to intersect at the 0.4 hour. Okay. So somewhere here. Okay. So 0.4 hours, so that will be about 24 minute. So you get the initial time, assuming that the temperature were 1100 degree centigrade, would be 24 minute. Now you are oxidizing it for additional 33 minutes. So the total time that you are giving is 57 minutes. Now if you again go to the oxidation chart for 57 minutes 1100 degree centigrade, you can draw a horizontal line, and this value you can read from the table. So that will be about 6500 angstrom. So the final thickness of the oxidation layer would be 6500 angstrom. Okay. So that is something that you can also see from the oxidation table that we have here. So we found out that the time is about 57 minute. So it is about 0.95 hour. So if you draw a vertical line from here onto the 1100 degree centigrade and you draw a horizontal line from there, so you will get about 0.65. So here this value you will read it as 0.65 micron. Okay. Now so that is one approach. The second approach would be to predict the thickness from the Deal-Grove model. So you have this equation. Okay. Now at 1100 degree centigrade, you can also, there are tables available to give you the values of B and the ratio of B over A. So two such tables I will show you here. So depending on the crystal silicon, here in this case we are talking about 100 wafer. So depending on the temperature, okay, depending on the temperature and what type of oxidation you are talking about, either you are talking about wet oxidation or dry oxidation, you would have the value for B over A, and the unit is micrometer micron per hour, and you have a value for B, which is micrometer square over hour, micron square over hour. So you can find what is the value of A, right. So in this case for 1100 degree centigrade, if you draw a line there, okay, and onto the 100 silicon wafer and draw a horizontal line there, so you will get about 5 micron per hour is the B over A. And similarly if you do that to find the value of B, you draw a vertical line there and then you draw a horizontal line there, let us say this is about 0.5 or 0.6. So from these values you can using these two values you can apply to this equation. So B will be let us say 0.5 micron square per hour and B over A is 5 micron per hour. So from there you can calculate what is A is 0.1 micron. Now knowing the value of A and B, the initial oxide layer thickness is 0.4 micron, that is given, and so for to calculate the time, so for for pre-oxidized wafer T equal to 0. Okay. So we have not started doing the oxidation process. So in that case you have to find what is the time scale that you need to do it to grow this oxidation layer. So you can solve this with T equal to 0 in this equation. So you can find tau is about 24 minute. Now you are putting again 33 minute, you are doing oxidation for another 33 minutes. So T plus tau will be 57 minute. Now if you go back to the same equation and you put T plus tau as 57 minute, and plug in the values for B and A, because they are only dependent on the temperature and the wafer and the dry or steam oxidation, so they are not changing, so you can use the same values of B and A. Now if you use T plus tau as 57 minute and you solve that equation, you can find the final oxidation layer is about 0.65 micron, which is 6500 angstrom. So there are two approaches that you can use to predict the oxide layer thickness. One is by using the oxidation chart, the second one is by using the chart where you can find the value of B and B over A and use Dilgrove model. Okay. Now let us look at thermal evaporation. Okay. So many times you need to metallize the surface of a substrate with some electrode patterns to build microfluidic devices or other micro devices. The one of the widely used technique for metallized wafers is thermal evaporation. It is one of the old technique that has been used in semiconductor industry, and it is also used to fabricate micro devices. Okay. So thermal evaporation, as I said, it is the oldest thin film deposition techniques, and which relies on boiling off or sublimating of heated material. If you heat solid at certain condition, at certain temperature, in certain way, it will directly go and become wafer. Okay. Instead of going into liquid and going to gas, it will directly become wafer. So that is called the sublimation process, and it is possible to achieve boiling of or sublimation of metals easily if you create vacuum condition. Okay. So typically in a thermal evaporation furnace, the temperature that is required is 600 to 1200 degree centigrade, and the vapor pressure would be around 0.1 torr, and these are some of the metals that are typically used for thermal evaporation: platinum, aluminum, silver, gold and titanium. Now from thermodynamics, the number of molecules that will leave a certain area of the evaporant per second is given by the flux. Okay. So you would know the flux is representative of how many molecules are leaving a particular target and going and falling onto the substrate. So F is N0 into exponential minus phi E over kT, where N0 is a slowly varying function of temperature and phi is activation energy. Okay. That is intrinsic of the metal that we are trying to evaporate, and so it is related to the enthalpy of formation of evaporant. T is the temperature and K is the Boltzmann constant. Okay. So typically in labs, metal is evaporated by passing high current through a highly refractive metal containment structure, typically a tungsten boat or a filament, and this process is called resistive heating. So as you see here, the metal that we want to evaporate will be present here. So this is the metal that we are trying to evaporate, and you have a highly resistance wire here, and you apply a high voltage using a power supply, and when you do so, this metal will evaporate. Okay. And everything is enclosed in a chamber connected to a vacuum system, and here you have a platform that will support the substrate on which you are trying to evaporate and deposit this metal. So the metal evaporates and coats the surface of the wafer here. Okay. So the metal will evaporate, and in wafer form it will come and get deposited onto the top surface of the substrate. So the resistive evaporation process using resistive heating is relatively simple as compared to other techniques that we will see, but one downside of this is it would spread the contaminants that are present in the filament, since the metal will evaporate and it may interfere with the filament itself while it evaporate, that may bring in contaminants that are already present in the filament. Okay. So that is one issue that we see in thermal evaporation, and the second issue is the filaments that we typically use are smaller in size, so the resistance, so that the resistance is higher, and but the small size of the filament would limit the thickness of the film that we can bring in on the surface of the substrate. Okay. So the thermal evaporation is used in the lab setting, and whereas in industrial applications what we use is called e-beam evaporation. Okay. So in e-beam evaporation, if you look at the setup here, typically we would have the metal that we want to evaporate or deposit onto a substrate in a crucible. Okay. So this is a crucible made out of ceramic materials, and we would be constantly cooling this crucible, and here we would have a high voltage power supply connecting to the crucible as well as to an electron beam gun. So high energy electron beam gun will be generated using high power, high voltage, and these electron beams can be projected, directed towards the metal present on the crucible using a magnetic field. So that is called magnetic focusing. So when these high energetic electrons will fall onto the metal will get vaporized and it will coat on the substrate. Okay. So that is the principle, and the electron beam based thermal evaporation, it results in good quality film because we are not talking about any filament here, the metal just evaporates, and in fact the metal itself, part of the metal where the electron beam is coming and hitting the metal, there itself it evaporates, and the other part of the metal form the crucible. So there is no contaminant that is present in this e-beam evaporation method, and but the other advantage is that the deposition rate of the e-beam evaporation is between 50 to 500 nanometer per minute, which is higher as compared to thermal evaporation. But the downside of e-beam evaporation is the setup is expensive, and you would need sophisticated arrangement of a magnetic focusing of the electron beam onto the metal. So if you look at thermal evaporation, when we look at how the process works. So the rate of at which the atoms or the molecules are lost from the source or the metal source due to evaporation, the flux F is represented in this way, which is dependent on the vapor pressure of the evaporant PVT, and it is also dependent on the temperature. Okay. So these are two parameters which affect the flux at the rate at which the molecules or the atoms of the metal are lost from the source and they fall onto the substrate. It also depends on the molecular weight of the evaporant. Okay. So the flux is directly proportional to the vapor pressure and inversely proportional to the square root of the molecular weight and the temperature. We can define a mean free path of these atoms, how they are removed and how they go and fall onto the substrate. The mean free path is expressed in this way. It is dependent on the gas constant, temperature, molecular weight, the viscosity of the gas and partial pressure. Now let us say in this example, if you see here, let us say this is the surface of the substrate and here you have photoresist pattern. So these areas you do not want to evaporate, and you want to put the metal, evaporated metal, on these areas, and here is the source, okay, and they are at an angle, okay. Now how do we determine the arrival rate, okay, the evaporated metal coming out of the source and reaching here, the arrival rate will depend on the angles, okay, the angle between the vertical to the line connecting the source and the substrate, okay. So it will depend on the cosine of that angle cos theta, and would also depend on the angle between the connecting line and normal to the wafer, beta, cosine of beta. So the arrival rate is proportional to cos beta and cos theta, and inversely proportional to the square of the distance between the two, the source and the substrate. And imagine if they are facing each other like parallel, where this is the source and this is the substrate, beta and theta will be 0. So the arrival rate will be inversely proportional to the square of the separation distance. Here you see the source is somewhere here, the source, the metals are directed towards the substrate in this way, and on the surface the surface have different topology, okay. So one surface is normal to the source, that source of ions that are coming, and but it also has other surfaces which are at an angle, okay. Let us say beta 2 is an angle of those two inclined surfaces, and for this surface the beta 1 is 0. So the thickness of the metal layer, evaporated metal layer, that we end up with T1 over T2 will be cos beta 1 over cos beta 2, okay. So the thickness would depend on the orientation of the substrate with respect to the metal source, okay. So with that let us stop here.